Gather around, children, and grab a cup of cocoa and a healthy snack because it is story time. Right. The year is 1968. It's groovy hippies and counterculture, um, summers of love and whatnot. Computers are very, very rare. They're in research institutes and universities and take, if not a whole room, at least the size of a fridge. And the most powerful computer on Earth is actually orbiting the moon. It is the AGC, the Apollo Guidance Computer, which is a computer that guides Apollo. Of course, I've mentioned the moon. We are talking about the Apollo missions. In 1968, the AGC is on board Apollo 8. Apollo 8 is the mission that that really won. Apollo 8 is the mission where the US really won the space race because they were able to send the capsule with people in it, crazy, around the moon and safely back. From then on, landing is a mere detail. Like this is really where progress was made. So Apollo 8, we are a year before the moon landing, right? And the moon landing is Apollo 11. So we are three whole Apollos before. This is Margaret Hamilton. She is still alive today. She's born in 1936. She is pictured here on board the simulator. That's a replica, or actually a copy more than a replica, of the actual Apollo module, but on the ground, so that they can test the hardware and the software and the astronauts like all together in the same context. A little bit about Margaret Hamilton. She studies maths. She does a bachelor in math in the 50s. You can imagine what it was like studying maths as a woman in the 50s. And then, just as she's about to embark on a fully funded scholarship for a PhD program in maths, she gets poached by NASA, who asked her to help with the software, work at MIT to do the software for the moon missions. Now, at this point in time, computer science and software engineering were not yet courses to be taught, or indeed disciplines to be named. That's the interesting part. It was sort of seen as applied mathematics before going to NASA. Margaret worked with Lorentz, considered one of the fathers and founders of modern chaos theory. They worked on weather prediction using computers. And in fact, again, Margaret's software was instrumental to Lorenz's results. An interesting part as well about like disciplines to be named. Software engineering was not considered engineering because Hamilton herself started using the term software engineering during the early Apollo missions. But software development was not taken seriously compared to other engineering, that is, hardware engineering. So the men wanted the high status, high prestige job, which was to do with the hardware, the solderings and the copper and metal, the big rocket. No need to be a Freudian psychoanalyst to see there's something going on there. So yeah, software engineering was not regarded as engineering, was not regarded as a science. Hamilton was concerned with legitimizing software development as an engineering discipline. This is very important to me as I am a software engineer, and I can only call myself a software engineer thanks to this particular female, as it happens, software engineer. This is actually not a story about Margaret. This is a story about Margaret's daughter here on the left, Lauren. In 1968, she's about 9, 10, maybe 8 at a push. 9. Let's call it 9, right? And well, I will let Margaret tell the story in her own words. I won't do a silly voice though. My daughter Lauren would often come to work with me at nights and weekends because we are all so dedicated. There wasn't a time where we weren't working. So in 1968, Margaret, who is 32, is just recently divorced. And the reason she has to take her kid to work is that the provision for childcare, there's an inherent sexism in the thing that, like, the divorced husband doesn't have the problem. The divorced wife needs to find a place to keep the kid busy. Anyway, she liked to play astronaut because she saw me playing that way in certain simulations we would run, like the picture before. This was in a hardware simulation because we wanted to try how the software worked with all of the other things, the astronaut, the hardware. That's called integration testing. So I remember one time when Lorentz simulation crashed, and I thought, OMG, how did that happen? We checked it, and she had done something the astronaut was never supposed to do. Because once you lift off pre launch, you are now on the way. She selected Program 1, which was the pre launch program, but she selected that during the mid course flight. So I went back and looked at the listing. So back then, you would print out the computer code on a listing, and sure enough, that would be possible. So I brought it to the people, whoever was involved, inevitably those were men, I can tell you that, saying, "This is amazing, look what happened." I don't know which people at NASA or MIT said, "Well, it's never going to happen because the astronauts are so well trained. It's just not going to happen." I said, but what if it does happen? My whole emphasis was always, what if, right? I wanted somebody to make the error detection recovery code saying, hey, that's not the right time to select program one. That's what the code would do. But they, again, the men, they kept saying, it's not going to happen. So I wrote a program note. So program note, that's not the code, that's the documentation, right? So I wrote a program note because that becomes part of the spec. So the astronaut knows it's there. They can find it. And the program note simply say, do not select program one during flight. And that's what the note said. Well, okay, I think we can all guess what happens. Those are the astronauts, the men, on board Apollo 8. You can see they're very well trained, right? A good boy astronaut. They're very well trained. You point them to the moon and you say fetch, and they go and fetch the moon for you. Well, their well training notwithstanding, boom. That is again Margaret speaking. Well, the very next flight, Apollo 8, that's exactly what happened. So one of the astronauts set it in program one. They had to restart the computer. Now, can I? Yeah, I'm going to go back a couple. Yeah, okay, that's the thing. The interesting thing about the Apollo program, and laser pointer, yeah, I get it, right, is that whilst they're over here, they're in the shadow of the moon and they can't speak to the Earth. They don't have line of sight communication with the Earth. So this is the worst possible moment to have a bug in your computer that requires the computer to restart. And yet it happened. And thanks to Lauren, we knew about it and we knew how to recover from that bug. So after that, they said, yes, Margaret, you can put that change in there. So it did get in there for the very next mission. So I think there's a moral to the story. Ask yourself what if. Trust the code, not the user, right? If there is a wrong way to do something, do not let the code allow it. There is also a sort of cultural and gender, moral here to take away is that, like the manager men were not, didn't accept, didn't want to put the change that the software engineer woman wanted to put in, thanks to a bug that was detected by her child, her daughter. So this is about, it's not so much about gender, it's more about diversity, having different ways of thinking. So the men, because they know about doing the right thing and they focus on the training, they don't even consider the wrong thing. It takes a kid, someone who's naive, someone who's doesn't have all of this kind of like pre-existent knowledge that in fact restricts what they're going to try, and they're going to try everything, and they like that implicitly children also make the best software testers because they want to click on everything, touch all the buttons, and you'll see whether your code works or not. So having a team where there are different types of people that think in different ways, whether it's male, female, or any other thing, gives you better outcome because then you will cover all the bases and write better, safer, more robust code. So this is what we now call robust programming. You program in a fashion that resists certain types of uses, or also called defensive design, right? So like you design in such a way that like you don't get attacked, you do not let yourself open to the possibility of the user creating an error or a bug. That was this week's story time. Thank you for